Fourier transform. Now we have to define the Fourier transform. So let us recall one things that in general integral transform, that is, if we define it as I of fx is equal to integral x1 to x2, that is the limit, k alpha x is the kernel operating with fx dx, and if we considering that this kernel is 1 by root over of 2 pi e to the power I kx, and the limit of the integration is stick to the domain of minus infinity to infinity, then is the range of the integration. Then this integral transform, general integral transform, can be replaced as Fourier transform f of fx is equal to 1 by root over of 2 pi minus infinity to infinity e to the power I kx fx dx. Here clearly this I kx is defined as the kernel of the Fourier transform, but here we consider only the parameter alpha, but this parameter alpha is already replaced by parameter k, so we can also written it as f of k is equal to 1 by root over of 2 pi minus infinity to infinity e to the power I kx fx dx. And one more thing is important, where k is real. Now this integral, if we observe that this integral is an infinite integral, so we must have to know the integral exists or not. But in the specially Fourier transformation, it is provided that the integral exists. That means we assume the integral is exists, and if fx is integrable in any finite interval, then since the integral exists, then fx, if fx is integrable in any finite interval and integral minus infinity to infinity fx dx is absolutely convergent, and since fx is integrable in any finite interval, so we can say fx into e to the power ik is also integrable in any finite interval. Okay, and if that means in any finite interval means that the same interval we consider, and if minus infinity to infinity absolute convergence means mod of fx dx is convergent, since because why this is convergent, now we are considering the inequality minus infinity to infinity more fx dx minus infinity to infinity fx e to the power I kx dx is less than equals to minus infinity to infinity mod of fx into mod of e to the power I kx dx, that is less than equals to minus infinity to infinity mod of fx dx. But why these things happen? Clearly we know that e to the power I kx equals to cos kx plus I sin kx by de Moivre's theorem. So mod of e to the power I kx is equal to 1. That means we are using this inequality, and it is clear that this will be 1. If this will be 1, we get this. And if we assume that this is absolutely convergent, that means it is bounded. So here we also find this is a boundedness of the function. That means here it is also convergent in any finite interval, and it is integrable also. Now we are discussing with one condition, that is called dirichlet condition. And now what this condition is? This condition is called Dirichlet's conditions. A function fx is said to satisfy Dirichlet's conditions in an interval AB in which it is defined if it satisfies the following conditions. What the condition is? Number 1, fx is bounded and the interval can be broken up into a finite number of subintervals each of which fx is monotonic, that is monotonic. And second condition is fx has only a finite number of maxima and minima in AB, and a finite number of discontinuity in AB. So we have already write these conditions, which condition will satisfy the dirichlet. That means here it is bounded, there is a finite number of cases, but in the Fourier transform it is obvious and clear that this condition satisfy the dirichlet condition, and we write from the definition that the integration of the Fourier transformation that runs from minus infinity to infinity. So clear and obvious, the function fx satisfy Dirichlet's conditions where in minus infinity less x less infinity, and the integral minus infinity to infinity fx dx is absolutely convergent. Then the integral fk is equal to 1 by root over of 2 pi minus infinity to infinity e to the power I k x dx fx dx exists. That is Fourier transform of fx dx exists. So we already today discussed the existence of Fourier transform and definition, how is it come from the general integral transform. Thank you.